The most telling sign of ancient gold movement isn't a glittering flake or heavy pan. It's a scarred, jagged rock surface that almost everyone steps over. In regions once rich with placer flow, textured bedrock can act like a fossilized riverbed, recording the turbulence and load of past high-energy water events. Smooth bedrock might feel more appealing underfoot, but it's the rough surfaces, where channels once clawed through soft host rock, that often point to hidden caches of ultrafine or flour gold. When gold-rich waters move with force, they abrade the path beneath them differently depending on the hardness of the substrate. Shale, schist, or even decomposing granite may develop deep crevices or jagged breaks where dense particles, especially gold, get trapped and settle. These aren't random fractures. They typically align with paleoflow direction, angle into the channel's base, and contain compacted layers of silt, black sand, or rust-colored sediment. In field terms, if the rock bites your boot tread and feels like a cheese grater under the palm, it's a candidate. This is the kind of terrain that can't be read from satellite maps or simple topography. The real clues lie at the microscale. In a recent foothill range revisit, hobbyists reported no surface color, but overlooked a quartzite ridge where pocked hollows, some only half a centimeter deep, had collected compact black sands beneath the dust. One rinse in a pocket pan revealed 3 microflakes per tablespoon of material. That density isn't a mother lode, but it indicates upstream or nearby retention worth investigating. The presence of coarse mineral coatings, manganese staining, red iron crusts, or clay cement also supports past gold-bearing flow. These coatings help trap heavies by reducing hydraulic washout. The tighter the crevice and the more difficult it is to clean by hand, the more likely it has resisted centuries of erosion. The downside: gold finds here may be invisible and less concentrated. In early reconnaissance, a magneton stick becomes invaluable. Skim it just above the surface, not dragging in soil, to pick up loose magnetite and ilmenite. Where these cluster thickest on fractured surfaces, it often correlates with gold settling zones. But magnetism alone can mislead. It's a helper, not a guarantee. If the rough surface seems barren, try a 5-10 cm scrape and pan sample from its lowest pocket. Even one color at this stage justifies a broader pass. Most importantly, document the texture. Grainy versus slick, angular versus water-rounded. These differences will help you choose between decoy and deposit as the terrain changes. A polished rock face may feel like the footprint of ancient flows, but in gold-bearing terrains, slick surfaces are usually dead ends. Smooth bedrock often signals active abrasion, where lighter sediment has recently scoured the rock clean, while rough, angular zones indicate historical turbulence and gold trapping potential. Knowing the difference means distinguishing between where gold has been flushed away and where it may have quietly settled. On first glance, a smooth surface can appear promising, especially when it runs parallel to modern watercourses. But unless that polish is paired with crevice features or residual black sand in nearby fractures, it typically reflects recent seasonal runoff rather than ancient gold movement. Real indicators lie in contrast zones, where a smooth slope gives way to pocked or jagged rock. That transition zone often marks a velocity drop in paleoflows, a sweet spot for gold deposition. Field confirmation comes down to reading microtopography. Along slick surfaces, look for patches of undisturbed moss or silt accumulation. If you find none, and the surface is clean even after the dry season, it's likely too active. Anything heavy, including gold, has already been swept downstream. But if there's a pocket of darker sediment clinging to a lip or depression in the transition zone, that's your cue to test. A classic setup is a flat, smooth slope followed by a jagged lip that dips into a concave basin. These trap zones, often just a few centimeters deep, can accumulate heavies during high-energy floods. Use a crevice tool or even a flathead screwdriver to peel back the upper sediment layer. If you hit a rust-colored, clay-bound layer or smell sulfur or iron, you've likely reached ancient pay layer residue. Density intuition helps here. Even if the pan shows minimal visible gold, Weight in hand of a tablespoon of the concentrate compared to local sand can be telling. Black sand mixed with tiny garnet fragments and a notable drop rate in water usually indicates worthwhile heavies. From here, you can either run the material through a mini sluice or store it in a sample vial for lab-scale wash later. There's also a color trick. Tilt your pan under low-angle sunlight or a headlamp beam. While pyrite sparkles, real gold will appear as a dull, buttery yellow without flashing silver. On slick surfaces, that sheen rarely appears unless gold has recently redeposited. But just a meter upslope, in that first rough catchment, fines can still cling invisibly. The presence of fractured bedrock means little unless the breaks work in your favor. Some splits drain gold, others catch and guard it for centuries. Most field collectors miss this nuance, assuming any crack or crevice offers equal opportunity. But in reality, the angle, depth, and orientation of fractures determine whether gold was captured or carried past unnoticed. To read them correctly, start by identifying the dominant flow direction of the paleochannel. You won't always see this on the surface, but alignments in rock striations, driftwood patterns, and sediment layering often hint at prior water movement. Once you've established a rough flow axis, inspect how the fractures intersect it. Fractures that cut across the flow at steep angles, especially those with downward opening, V shapes, are prime gold traps. These act like natural riffles, slowing water just long enough for heavy particles to fall out and settle. Longitudinal cracks running parallel to flow may collect some material but are often flushed clean during peak flow events. In contrast, transverse fractures intersecting the flow, especially when paired with drop-offs or concave basins, tend to hold compacted sediment, iron oxide buildup, and heavies beneath the visible layer. It's these intersections that are worth the effort of careful cleaning and testing. The size of the crevice matters, too. Narrow, deep fractures around 1-3 cm wide are ideal. They're just tight enough to prevent reentrainment of gold particles during floods, but wide enough to insert a crevice tool or nozzle for extraction. If a crevice contains angular quartz fragments or clay that resists flushing even after a rain event, it likely hasn't been disturbed in decades. That increases the odds of fine or flour gold accumulation, especially below the upper oxidized layer. Tools make a difference here. Start with a stainless crevice scraper, then graduate to a vacuum-assisted nozzle or high-suction snuffer for ultra-fines. If the crevice plunges deeper than hand tools can reach, consider a wet-dry vac rigged with a HEPA filter to avoid releasing fine dust. Some field operators use modified aquarium tubing and mouth suction for delicate extractions, though this carries health risks if mercury or arsenopyrite is present, common in older gold zones. In one foothill creek tested last season, an overlooked fracture set at a 45-degree angle to the stream flow, roughly 7 wide and just under a meter long, yielded 6 flakes in its lower third after a light rinse and vacuum extraction. The upper portion, although similar in appearance, had been smoothed by flash floods and carried no visible heavies. This highlights the value of probing depth and flow resistance, not just surface appearance. Even if gold isn't immediately visible, don't discard the fine sediment from well-positioned crevices. Dry and store it in labeled bags for gravity separation or lab panning later. And keep a notebook. Fracture orientation and yield patterns often repeat across similar bedrock formations, creating predictive models for future sites. No matter how promising a fracture looks, real progress begins with a disciplined first pass. Fast, light, and aimed at collecting diagnostic evidence rather than full recovery. Many prospectors spend hours picking apart a single crevice, only to find a dusting of iron sand and no color. But with the right tools and sequencing, you can vet multiple sites in under an hour and narrow in on zones where gold truly lingers. Begin by flagging test points across a rough bedrock stretch, ideally targeting a range of fracture angles and sediment types. Use pin flags, bright tape, or even GPS waypoints to track each crevice or depression sampled. The goal is repeatability. If you find color, you'll want to return under different conditions or with better gear. Random scooping without notes wastes more gold than it finds. Your first tool should be a crevice scraper or hooked probe, chosen to match the width of the fractures. Pry out the darkest, most compacted material from the bottom of each crevice, typically the lower 5-10 cm. If that layer contains clay or oxidized material, prioritize it. Above that level, lighter debris is usually more mobile and less likely to trap heavies. Once material is removed, pass a magnet just above the cleared crevice. No contact. This sweep helps detect fine magnetite and ilmenite grains, useful indicators of placer zones, but don't rely on them alone. The key is to distinguish between magnetic heavies and true gold potential. In gold-bearing areas, magnetic sands tend to peak just upstream of gold flakes, often clustering where flow slows slightly, like at the inside corner of a bend or below a waterfall lip. From your collected sediment, isolate a tablespoon into a pocket pan or finishing pan and add just enough water to swirl gently. Watch for fine silt washing off in the first 2 tilts. Then, as you swirl heavier material into the bottom ridge, observe the behavior. Even a single yellow speck, resistant to movement and hugging the pan rim, can justify further sampling. For better contrast, test under angled sunlight or use a directional headlamp. This minimizes mica reflection and exaggerates the buttery sheen of fine gold. Don't be discouraged if the color is barely visible. If the concentrate includes thin flakes that flatten rather than spin or float, or if a particle leaves a yellow streak when rubbed on stainless steel, it's worth noting, even if it seems minor. You should aim to test at least 6-10 distinct fractures in a 10-meter stretch during a first pass. Record sediment color, magnetite content, and any visible fines or flakes. Then rank each site: high interest, visible color or high black sand concentration, medium good trapping geometry but no color, and low washed out, shallow or loose. Only return for full extraction on high interest zones. A well-structured first pass also helps avoid bias. What looks good visually may not hold value, and what seems unremarkable, like a narrow horizontal crack tucked beneath overburden, might be a hidden pay streak. Speed, consistency, and documentation matter more than instinct alone. The second testing round often defies expectations. A crevice that gave up a promising flake in the first pass can go silent, while a previously dull fracture lights up under thermal or magnetic scrutiny. This is where low-cost tools earn their weight, revealing patterns invisible to the eye and helping to confirm whether gold once concentrated there, or if your earlier success was random. One of the simplest second-pass tools is a UV flashlight, ideally long-wave, 365 nm, with a filtered lens to cut visible light bleed. While gold itself doesn't fluoresce, its mineral companions sometimes do. Scheelite, calcite, or fluorite veins embedded in fractures can glow pale blue, purple, or pink under UV, hinting at hydrothermal pathways where gold may have mobilized. If a fracture contains fine quartz grains with UV-reactive minerals at the edges, that's a subtle but useful vector. More telling, however, is a shift in temperature response. Thermal conductivity testers, while often used for gemstones, can also be applied to metallic traces in rough concentrates. By placing a cooled probe against a dry flake, true gold will rapidly conduct heat away, mimicking the response of silver or copper alloys. In contrast, pyrite or mica will respond sluggishly. Field models like the Presidium tester can detect this change, though sensitivity to ultrafine gold remains limited. Still, if you've collected visible flakes or grains, a thermal check can provide another point of confidence. The magnet remains a workhorse in this round, but now it's used for exclusion as much as attraction. A neodymium magnet wrapped in plastic can sweep over dried concentrates. If your gold lifts even slightly with the magnet, it's likely misidentified. magnetite, hematite, or certain alloys. But if particles stay put, especially in clustered zones from your earlier flagged sites, it's worth expanding your dig. Remember, true gold resists magnetism entirely unless artificially alloyed. For borderline cases, use a water drop test. Place a tiny flake on the tip of your finger or a flat rock and drop water onto it. If the flake holds position, flattens, or adheres to the surface, it's probably gold. Mica and pyrite tend to roll or spin, betraying their lighter density. This behavior difference becomes clear when done side by side with known black sand. At this stage, your sample profile begins to evolve. You're no longer looking at individual flakes, but clusters, patterns, and consistency. Does gold appear only in one crevice orientation? Does its presence correlate with a specific mineral matrix or depth level? Plotting these against your earlier sample ranks builds a working map, a crude heat map of potential pay zones. Moving from scouting to systematic recovery isn't just a matter of scale, it's a shift in discipline. This is the point where many hobbyists plateau, mistaking a few successful pans for a viable deposit. But gold distribution in rough bedrock is rarely linear or uniform. Without a structured workflow, you risk extracting from barren zones while skipping over subtle hotspots. Precision at this stage is everything. The first decision is grid layout. Choose a workable unit size, typically 1x1 meter squares, and mark them clearly using chalk, paint, or rock piles. Orientation should follow the dominant paleoflow axis identified in earlier steps. Within each grid, note the dominant bedrock type, crevice frequency, sediment depth, and previous test results. Even two adjacent squares may yield radically different outcomes, especially in turbulent depositional zones like boulder fields or channel bends. Once gridded, start with a standardized sieve process to eliminate the noise. Use 20 mesh, approximately 0.85 m as your primary classifier to separate coarse overburden from concentrate-rich fines. For ultrafine potential, pass the sub-20 material through a 40 mesh, approximately 0.425 m. This dual pass lets you isolate the most relevant fraction, where flour and fine flake gold tend to concentrate. Work dry whenever possible for weight efficiency, but switch to wet sieving in clay-rich or cohesive sediment zones. Now pan only a representative sample from each grid, typically 1 to 2 liters of classified concentrate. Keep water volume and panning style consistent to maintain sample integrity. Document black sand percentage, visible color, and any unusual behavior, such as floating flakes or persistent garnet clusters. Over time, these grid results produce a recovery contour, a map of where heavies trend and where they taper off. High-confidence zones, those returning visible gold from multiple samples, should then be flagged for full extraction. Here, deploy more aggressive methods, crevice vacuums, snuffer bottles, and sluice boxes with microriffles. If water access is nearby, set up a mini sluice in a controlled outflow. Monitor tailings with a magnet and inspect under UV to confirm recovery efficiency. Equally important is your spoil management. Always store removed sediment from high-value crevices in sealed bags or buckets for later processing. In historical placer zones, a single overlooked microlayer can carry more value than the entire upper bed. Label by grid and layer to preserve context, especially if lab assay or resale is the goal. Nothing derails a recovery operation faster than a false positive. Many prospectors, even experienced ones, have chased glitter that turned out to be worthless. Mica, pyrite, or high-sheen silicates that mimic gold's luster under field conditions. These imposters can survive early panning, mimic the heft of real gold and magnetite-rich concentrates, and even fool the eye under directional light. But a few practical tests in the field can eliminate these decoys before they cost you hours, or worse, fuel misinformed investment. The most common culprit is mica, especially muscovite or biotite in flaky, layered forms. These often settle into crevices during floods and show a deceptive golden glint in sunlight. In panning, mica flakes behave erratically. They flash, flutter, and float with minor water movement. Real gold, by contrast, resists flow, stays tight to the pan bottom, and dulls under shadow. The critical test here is behavior. Swirl your concentrate gently and then pause. If the flake shifts position after you stop moving, it's not gold. Pyrite iron sulfide is more convincing. It's dense, metallic, and holds its shape. But under magnification or loupe, its crystal habit gives it away. Gold presence is amorphous or ragged-edged, while pyrite forms tight cubes or facets. Pyrite also crushes brittle, snapping into shards, whereas gold will flatten like soft foil. This test requires care. Always wear eye protection and avoid inhaling dust. Crushing is best done on a steel plate with a smooth-faced rock. If the sample powders or shatters, gold it is not. Another common deception comes from translucent silicates like feldspar or clear quartz chips that have weathered smooth. These can take on a golden hue when stained with iron or manganese oxides and partially buried in black sand. But under backlight or oblique angle, they flash clear or white. Gold never shows translucence. It's always opaque, even in microflake form. To build certainty, you can combine two simple in-field tests, streak and float. For the streak, rub the particle across a stainless steel or unglazed ceramic surface. Real gold will leave a dull yellow streak, while pyrite leaves a dark or greenish-black trail, and mica won't streak at all. For the float, drop the suspect flake in a still water container. Gold sinks and sticks. Mica and lightweight silicates often float or take a circuitous path to the bottom. A subtler challenge arises when heavy minerals cluster, especially when black sand is intermixed with garnet fragments, zircon grains, or small corundum particles. These create a deceptive sense of density. You might feel weight in the pan, but without visible gold, it's just a heavies-rich zone, not a pay streak. The trap here is confirmation bias. Assuming gold must be present because everything else lines up. That's why repeated absence of color, even with good heavies and fractured geometry, is a red flag. Field intuition can only take you so far. When flakes blur the line between real and mimic, it's density, not luster or behavior, that seals the case. Gold-specific gravity, roughly 19.3, makes it over 7 times heavier than quartz and more than twice as dense as many other heavy minerals. If you want to separate out truth from false positives and prioritize your best samples, you need to measure displacement, even in rudimentary form. The simplest, reliable method is a water displacement test using a graduated vial or syringe. First, dry your suspect sample thoroughly. Even a trace of moisture skews the result. Next, fill a narrow measuring container with water to a known line, say 10 ml. Carefully add your flake or nugget, ensuring it's fully submerged without trapping air bubbles. The new water line gives your total volume. Subtracting the original gives the sample's volume in milliliters. Then weigh the sample in grams using a pocket scale. The math is direct. Gold will return a value between 18.5 and 19.5 in most field conditions. Mica, quartz, and even pyrite typically fall below 5. Even if your measurement tools aren't lab-grade, the gap is so wide that you'll still get a clear separation between true gold and common deceivers. If you're dealing with ultrafines or flour gold that can't be picked up or weighed singly, batch testing becomes viable. Use a small vial to collect all visible color from one crevice or grid square. Let it settle, then dry, weigh, and measure the displacement of the entire sample. This gives you not just confirmation, but a rough idea of total mass per grid, which becomes critical when estimating deposit potential. One common mistake at this stage is over-reliance on heft in hand. While gold does feel heavy, so do magnetite clusters or garnet-rich sand when wet. The human hand can't reliably distinguish between 3 and 19 specific gravity, especially when samples are small. That's why repeatable tests, even crude ones, should always trump instinct. For especially fine material, flour gold and dust, you can use a settle tube to estimate concentration potential. Fill a transparent tube with water and your dried fine concentrate. Agitate gently and watch the layers form as particles settle. Gold will drop first and fastest. If a distinct bottom layer forms within the first few seconds and remains separate from the black sand, you're likely dealing with a gold-bearing sample. This won't give exact density, but helps estimate pay viability across larger batches. Field density testing also flags unusual finds. For instance, if a flake behaves like gold but reads 16, 0, 17, 0 in specific gravity, you may be looking at an alloy, possibly electrum, a natural gold-silver mix, or even a high-grade brass counterfeit. These outliers demand lab testing before any value is assumed. At some point, the most valuable gold in your field area is what's visible. It's what lies just beyond current reach. That's when mapping past hydrology becomes essential. Gold doesn't travel far, but it follows rules: gravity, turbulence, and time. By overlaying your surface grid with reconstructed channel paths, you can anticipate where the heaviest concentrations likely settled, even if erosion or human activity has since buried or obscured them. Start with topographic clues. Dry meanders, unnatural ridgelines, or U-shaped valleys often mark paleochannels, old riverbeds no longer in use. These tend to run above or parallel to modern creeks and are typically separated by only a few meters in elevation. A handheld GPS with terrain shading or a LiDAR overlay app like Gaia GPS or QGIS Mobile can help identify subtle depressions or terraces where ancient flow diverged. If your high-yield grid points cluster along a particular slope or line, that pattern may trace the edge of one such paleochannel. Sediment contrast helps verify these guesses. In modern creeks, you'll find light, angular rocks mixed with organic debris. But in paleochannel remnants, look for a compact gravel layer with well-rounded clasts, often under a meter or more of sterile overburden. The gravels may appear cemented or iron-stained, a sign they've been immobile for decades or centuries. This is classic false bedrock, where gold can pool above a clay hardpan or compacted silt, mimicking the role of true bedrock in trapping heavies. Test these zones with vertical probes or hand augers. Even a piece of rebar or a tile probe can feel the change. Soft fill gives way to dense, compacted material with a distinct crunch or resistance. Extract samples at regular intervals as you probe deeper, 10 cm, 20 cm, 30 cm, and record each by depth. The first sign of black sand or clay-bound gravels often signals you're entering the depositional zone. One strong tell: red to dark brown rust layer just above bedrock or clay. This iron-rich stratum acts like a shelf, catching gold washed down from upslope. Fine particles will often be embedded in the matrix, requiring sluicing or careful drying and classification to extract. Historical maps, if available, are invaluable here. Many 19th and early 20th century surveys note hydraulic diggings, diverted channels, or tailings piles, all of which mark human interaction with gold-bearing zones. These sites are often written off as worked out, but modern methods can recover gold missed by crude sluices and shakers, especially fines and flour. Overlay your prior field data, crevice scores, density results, magnetic sweep yields, onto your projected paleoflow map. Pay attention to anomalies. Why did one square near an apparent ridge yield color, while another closer to modern water stayed blank? Sometimes, gold migrates upward via capillarity in clays or downward through post-flood fissures, breaking expected models. But repeated anomalies along a certain trendline usually mean structure, not accident. The transition from field success to market evaluation brings a sharp reminder: not all gold is created equal. Just when samples start showing consistent yield, flakes, fines, even a few pickers, one lab test, one buyer's glance, or one legal document can unravel assumptions. Midpoint reversals like these are common in placer operations. The gold is real, but its story, purity, or provenance shifts the stakes entirely. One such reversal starts with composition. Field-tested gold, especially fines recovered from crevices or paleochannels, often carries impurities: silver, copper, or iron. This naturally occurs in alloyed forms like electrum or in sulfide-rich zones where gold forms in association with arsenopyrite or chalcopyrite. When sent to assay, such samples may return gold content far below visual estimates. A bright flake may assay at 70% gold, 20% silver, 10% base metals, reducing market value by up to 30% depending on smelter rates or buyer policy. Assay sheets tell the truth in hard numbers. For example, a 0.5 gram flake might only contain 0.35 grams of pure gold. That purity, often expressed as fineness, affects what refiners will pay. Raw placer gold ranges from 750 to 900 fineness, 75–90% gold. Unless you refine it yourself, expect deductions. Some buyers will offer only 70% of spot for raw gold below 850 fineness. Knowing this upfront prevents disillusionment at the sale table. Another midstream shock arises from ownership confusion. That promising stretch of exposed bedrock. It might sit inside an existing claim, even if no signage or recent activity is visible. Many placer and lode claims, especially under US BLM or Canadian systems, are maintained passively through paperwork and annual fees. Digging or removing material, even by hand, without permission can constitute mineral trespass. If samples were collected without checking land status, any commercial gain may be challenged, or worse, legally voided. To protect yourself, run a land status check before expanding operations. In the US, BLM's LR2000 database or Onyx Hunt app offers claim overlays. In Canada, consult provincial mineral tenure maps. Private property brings its own risks. Gold found on someone else's land, even if they're unaware, may be subject to surface and mineral rights division depending on local law. But perhaps the most humbling reversal occurs when a buyer identifies your gold by shape, composition, or micro-inclusions as originating somewhere else. In a few high-profile cases, gold dust allegedly recovered from the field turned out to be foreign flake from jewelry sweepings or recycled scrap, flagged by trace elements like palladium or tungsten. This not only voids legitimacy, but raises suspicion of fraud if resale is attempted at a premium. To preempt such outcomes, provenance documentation matters. Keep photos of the recovery process, GPS coordinates, sample logs, and assay receipts. If challenged, this paper trail can distinguish legitimate field recovery from suspicious resale or misrepresentation. When setbacks strike, be it an unexpected alloy, disputed claim, or undervalued offer, the solution isn't to retreat but to align with proven methodology. Institutional and professional practices offer a clear path forward. Standardized sampling, validated testing, and defensible documentation. These aren't bureaucratic hoops, they're the benchmarks that separate guesswork from legitimate field discovery. By adopting even a subset of these, you not only gain precision but credibility. Start with the sampling protocol. The U.S. Geological Survey, USGS, Canadian Geological Survey, and major academic field schools follow a core principle: reproducibility. Each testable area must yield consistent results when resampled under similar conditions. For placer gold, this means gridding, sieving, classifying, and recording recovery rates over multiple adjacent units. A single flake is anecdotal. 3 flakes per meter across 5 meters is a trend. If you plan to present findings to a buyer, partner, or lab, this repeatability becomes your best asset. For in-field classification, institutions standardize mesh sizes. 10, 20, 40, and 60 are common in professional-grade sampling. Each material class is panned, weighed, and recorded separately. While hobbyists often lump samples together, professionals track which size class holds the most gold. Often, surprising value lies in sub-hash 40 fines, which older equipment failed to recover. This level of granularity helps you model potential recovery at scale. When it comes to test verification, certified labs follow a chain of custody process. Sealed bags, labeled origin, date, and sample ID, often accompanied by a field log or digital photo. While you may not need full lab protocols in casual collection, mirroring their process adds serious weight to your findings. Simple steps like bagging samples with zip ties, photographing each site before and after extraction, and logging observations in a waterproof notebook establish a defensible record. Authority also comes from test method selection. Instead of relying solely on panning or displacement, institutions cross-reference with fire assay, atomic absorption spectroscopy (AAS), or inductively coupled plasma mass spectrometry (ICP-MS) for composition verification. While these are lab-bound, you can mirror the logic by sending your best concentrate for assay, especially if you're building a case for commercial viability. Choose labs known for placer work, and avoid those that only assay load ore or jewelry scrap. Even mapping protocols follow standardized logic. The grid sampling model used by mining geologists, sometimes called a systematic trench grid, lays out recovery zones in tight, numbered intervals. These aren't random guesses. They're based on terrain, flow direction, and previous test values. If you're planning to stake a claim, this map becomes your most important legal and strategic asset. In contested zones, well-documented field grids can tip court or arbitration decisions. And finally, respected institutions emphasize environmental and ethical compliance. Documenting how sediment was removed, how tailings were handled, and what restoration was done, if any, shows good faith and long-term awareness. This isn't just for regulatory optics. It's how responsible field operations earn long-term access and local trust. No matter how refined your technique, its success ultimately hinges on context: geological, climatic, and regional. Gold recovery in rough bedrock isn't universally viable. In some terrains, your best efforts will yield nothing but false indicators and barren fractures. But in others, especially where ancient turbulence met long-term stability, even the most unassuming surfaces can still produce. Understanding where your method works and where it fails is the key to scaling intelligently. The best regions for this technique share a few defining features: exposed or shallow bedrock, documented history of placer or lode activity, and signs of intermittent but forceful water flow. In North America, these include the Sierra Nevada foothills, California, the Salmon Valley region, Idaho, the Fraser and Caribou districts, British Columbia, and select parts of the Colorado Front Range. Internationally, similar terrains appear in Victoria, Australia, Otago, New Zealand, and the Ural Mountains, Russia. What unites them is a history of glacial retreat or hydraulic reworking that exposed fracture-prone bedrock to gold-laden flows. In contrast, heavily vegetated lowlands, thick alluvial plains, and swampy floodplains rarely yield to this method. Even if gold exists, it's buried under meters of silt, sand, and organic debris, beyond the reach of manual crevice tools or vacuum setups. Similarly, in terrains dominated by soft volcanic ash or unconsolidated sandstone, fractures may form but won't hold their shape under flood pressure. The lack of stable trap zones means gold, if present, keeps moving. Bedrock type plays a significant role. Metamorphic and igneous zones, especially those with schist, slate, or quartzite, are ideal. These rocks tend to break along cleavage planes or weather into angular, gold-trapping surfaces. Serpentinite zones can be productive too, particularly where talc or actinolite veins intersect. But beware ultramafic rocks in high-nickel or chromite zones. They often carry indicator minerals like magnetite or garnet but no gold. Field tests may glow with black sand, yet yield no value. Water regime also matters. Seasonal flash floods, common in arid or Mediterranean climates, tend to excavate bedrock and reset channels, allowing gold to settle in new fractures or old ones to be exposed anew. In contrast, continuously flowing rivers often scour bedrock clean, making gold retention unlikely unless armored by cobbles or clay. Even within a productive region, microlocation determines success. For example, the inside bends of dry creeks may seem ideal, but if the bedrock is polished or filled with modern sediment, they're too recent. Meanwhile, just upslope on a shelf or paleoterrace, iron-cemented gravels might hide undisturbed layers over fractured rock. That's where mapping pays off, especially when cross-referenced with historical dig records, LIDAR elevation models, or even old claim maps. Cultural and legal overlays add another layer of constraint. In some regions, like Alaska's 40 Mile District or Yukon's Indian River, legacy claims dominate, leaving little open access. In others, like parts of Arizona or Western Australia, open ground remains plentiful but comes with high permitting thresholds or strict environmental regulations. Ultimately, this method thrives in overlooked margins, too thin for mechanized dredging, too rocky for large-scale wash plants, yet too weathered for surface prospecting alone. In these zones, your refined grid, tests, and field rigor give you an edge. Not all gold behaves the same in the field. The size, shape, and alloy content of gold particles determine how and where they settle. When working rough bedrock, this distinction becomes critical. You're not just looking for gold, you're targeting specific forms most likely to lodge in crevices and fractures. Understanding these forms and their mineral companions guides every decision, from where to dig to how to test and process. Flake gold is the dominant form in creviced bedrock. These are thin, flat particles ranging from a few millimeters across down to near microscopic sheets. Their shape gives them a unique advantage: high surface area relative to mass, allowing them to plane down through sediment and wedge tightly into bedrock fissures. Once caught, they're rarely moved again, even in high-energy flood events. These flakes may appear bright yellow or dull bronze, depending on alloy content, and often require angled light to detect. Flour gold, finer still, is the most elusive. These particles under 150 microns often travel suspended in water for long distances before settling. They adhere to clay particles, organic matter, or mineral films inside bedrock crevices. Visually, they may be invisible in the field. But when concentrated, they impart a metallic sheen to black sand or form a dense streak in the pan's edge. Trapping flour gold demands tight crevice zones with clay or iron cement. Dry, fractured zones rarely hold it unless moisture once sealed them. Nuggets and coarse fragments, while more rare, behave differently. Their greater mass causes them to lodge quickly, often at the head of a crevice or beneath an overhanging lip in bedrock. They prefer abrupt drops, natural riffles, plunge pools, or bedrock steps. If you find rounded or water-worn nuggets, you're near or within a high-energy paleo channel. Angular pieces suggest proximity to the source vein or minimal travel, potentially indicating residual load material nearby. Each form of gold tends to associate with a different suite of indicators. Flake and flour gold commonly appear with magnetite and ilmenite in rough concentrates. These iron-rich minerals are dense and tend to cluster alongside fine gold in pan tailings or sluice mats. Garnet sands, especially dark red almandine, are also common companions, offering a helpful proxy for placer potential. If your pan shows these even without visible gold, you're in a candidate zone. Coarse gold often correlates with quartz fragments, ironstone, or manganese oxide stains. In some zones, it rides with galena or arsenopyrite, especially in areas near historic hard rock workings. These sulfides often break down slowly, releasing embedded gold over decades. If your samples contain metallic grains that oxidize orange or smell faintly of sulfur, test them carefully. Fine gold may still be embedded inside. False indicators abound. Zircon, rutile, and even spinel can appear in heavy concentrates and suggest value, but they lack any gold association unless you're sampling in kimberlite-adjacent zones, rare in placer contexts. Knowing when to ignore black sand and when to pursue it depends on whether it's magnetically active and whether gold shows up in even small quantities alongside. By aligning gold type with indicator suite and bedrock form, your prospecting becomes predictive. You're no longer guessing, you're interpreting a pattern of behavior, like tracking a fluid that moves by rules. Chasing gold into fractured bedrock can put you in some of the most volatile terrain a prospector will ever face. The same forces that expose rough rock, seasonal floods, slope failures, and erosion create hazards that require more than just caution. Without the right timing, tools, and permissions, even a promising crevice can become a trap. Responsible recovery begins with a sober look at risk and the legal ground beneath your boots. First, the terrain itself. Bedrock exposures are often found in river bends, dry gulches, and canyon narrows, all prime zones for flash floods. In arid or alpine regions, upstream storms can send walls of water downstream with little warning. Even in clear weather, water may surge from snowmelt hours after conditions change. Before entering a creek bed, especially between steep walls, always check the forecast upstream. Use satellite view or topographic apps to identify catchment areas. If there's any rain predicted above your work site, even 30 kilometers away, defer your trip. Slopes pose another risk. Bedrock near escarpments or in old diggings can become unstable, especially when undercut by erosion or saturated from recent storms. Rockfall isn't always signaled by noise. Many prospectors have been caught off guard by silent slab movement or crumbling overhangs. If you're working under an exposed face or cliff, assess rock integrity by tapping with a hammer. Listen for hollow sounds. Avoid standing beneath fractured ledges, and always plan your exit route before you start. Then there's access legality. In many gold-bearing regions, riverbeds are subject to complex ownership layers. A surface landowner may not own mineral rights. In the U.S., rivers flowing through public land may be open for casual prospecting, but only above the high water mark and not with motorized equipment unless explicitly permitted. In Canada, recreational prospecting is often allowed on Crown land, but claim status must be checked and environmental guidelines followed. To avoid trespass or seizure of recovered gold, check the legal status of your location before sampling. Apps like Onyx Hunt or local mineral registry portals can show active claims and land use zones. If working near protected areas, national parks, indigenous lands, or conservation easements, assume restrictions unless clearly stated otherwise. Violations can lead to fines, confiscation of gear, or bans from future access. Physical safety also extends to your gear. Carrying a crevice tool, vacuum hose, and classifier over rough terrain requires balance and free hands. Use a backpack rig or modular bucket system to keep weight distributed. A collapsible walking stick isn't just for comfort. It can test depth in murky pools or confirm solid footing on mossy bedrock. Always carry a trauma kit, and if working alone, log your coordinates with a contact before entering the field. Wildlife, too, can be a factor. In regions like British Columbia, Alaska, or Northern California, creek beds double as travel corridors for bears and mountain lions. Gold concentrates can carry fish or organics that attract scavengers. Store them sealed, and never leave pans or bags unattended. If you're in venomous snake territory, like the Southwest US or Australia, watch where you place your hands when reaching into crevices or under rocks. The jagged, fractured surfaces most people overlook, dull, uneven, unspectacular, often preserve more than ancient dust. They carry the geological memory of flows that once moved gold, tracing where time, water, and gravity conspired to concentrate value. When approached with method, patience, and the right tools, this seemingly lifeless rock reveals a silent, yet precise, map. Throughout this process, we've learned to separate gold from glitter, to read the language of bedrock fractures, to trust density over instinct. We've seen how flour gold clings to layers of clay and magnetite, how the shape of a flake tells its travel story, and how each indicator, no matter how subtle, fits into a larger pattern. Successful recovery here isn't luck or guesswork, it's discipline. Measure, classify, record, repeat. But we've also seen the boundaries, the physical risks of unstable terrain, the legal consequences of crossing claim lines, and the importance of documenting every step if you plan to move beyond hobby scale. The gold is there, but it won't reward shortcuts. It responds to proof. And maybe in the end, the richest find isn't the metal itself, but the sharpened ability to see what others miss. The rough surface, often stepped over, dismissed, or ignored, still holds stories in stone, waiting to be read. For those who learn the signs, it can offer more than shine. It can offer certainty.